Well, welcome everyone to GeoHug. So before we do kick off today's session, I would like to take this time to acknowledge the traditional lands which we're all coming from today. I live on the beautiful lands of the Gadigal of the people of the Aurora Nation, and I'd like to pay my respects to the elders past, present, and future. And yes, I'm very excited that we have Antoine Caté with us today. So Antoine is a structural geology consultant with SRK Consulting. He's an expert in the applications of data science and machine learning in geosciences, including for prospectivity analysis and automated core logging. So Antoine is the author and co-author in several peer-reviewed publications, workshops, and numerous presentations in economic geology and in applications of machine learning in geosciences. So it is going to be brilliant hearing his insights today on bridging geoscience and data science with successes and lessons from the industry. So I hope you all enjoy it today. And yes, thank you so much, Antoine, for joining. It's awesome having you here.
Yeah, thanks a lot, and thanks a million for the opportunity to present.
Awesome. I was really curious what got you into geology to begin with.
So that's going to sound a little bit corny, but that's simply I like to collect rocks when we were in hikes with my parents when I was a kid, and I never stopped liking doing that and continued collecting rocks until I asked my parents, well, what can I do to do something related to that? And we found the possibility to become a geologist, which I thought was like, okay, sounds too cool to be true. And actually, no, it's not too cool to be true. You can do that and get paid to do that and get paid to do to go to amazing places and collect rocks.
I love that so much. That is awesome. And so I imagine you have been collecting rocks in some pretty cool places. What have been some of your highlight geology spots?
I would say in terms of amazing geology, what I preferred were places where you have a lot of outcrops. So, for example, Morocco in the desert close to the Sahara, or
Yeah,
Saudi Arabia, where you have more outcrops than you can chew, and then you can do real geology. Yeah.
that is so awesome. And I know that you're traveling this week, so you don't have them with you, but you did take some pictures for me of some of your favorite pet rocks. Do you want to share your screen and show us what you got?
Yes, I will do that right now. So yeah, I'm several thousand kilometers away from home and couldn't take rocks with me, but I took some photos of rocks I have in my office. I took two photos of the same rock type or mineral, I should say. This is muscovite. So the first one right here, that comes from pegmatite. This is one muscovite crystal that's fairly big, super thin. It's so thin you can fold it. It looks a little bit like plastic. You wouldn't think it's an actual crystal. So I find this one is pretty amazing. I actually don't know where it comes from. This is for my first job as a geologist, which was sorting archives of industrial mineral company, and we were able to take everything that didn't have to be archived, and there are these amazing pegmatite crystals. So here we go. So no idea where it comes from, probably somewhere in France, but I don't know where exactly. And the second rock right here, same thing. This is mainly muscovite. This one is a muscovite schist that comes from the Lalor mine, where I did my PhD. And this time, instead of one crystal, this is a lot of tiny crystals. But the part I really, really like about it is the folding you have in it. So this is the folding of a foliation, and you can see that the little folds look like it's a fabric. So the rock was so incompetent during the formation. It folded like it was a soft fabric, and now it's a hard rock. So I really like the texture it provides to the rock.
That's awesome. Wow, they're very cool. Thank you for sharing them with us. And yeah, thank you so much again for joining. I'm really excited to hear from you today. So yeah, we can get started whenever you're ready.
This presentation, I didn't want it to be focused on one technical aspect or go too deep into the details of how data science algorithms and tools work, but more wanted to share some experiences, hard-earned experiences, I should say, and hopefully spark a discussion about it. So yeah, the title is Bridging Geoscience and Data Science, and Successes and Lessons or Challenges from the mining industry. So the first thing I'd like to give is a little bit introduction on what it's going to be or not be in this presentation. So I think most of us have seen that data science is being used more and more by geoscientists in exploration, mine geology work. But the term and other terms like AI, machine learning have been used quite a lot and for a lot of different things. So and to a lot of different effects. So most practices are either recent developments or they have been extensively not been extensively used in the past. So a lot of what we do in data science in geology in a more focused way, it's pretty new and we learn a lot. We do mistakes, and something that's industry or could be called an industry standard practice nowadays. Maybe in 2 years, it's going to be completely different. And there's no guidelines and best practices yet. So if you do a resource estimation, there are plenty of guidelines out there to tell you exactly how to do it, how not to do it. In data science, that's not the case. It still has to be built. That's an amazing place we are in time where we have the opportunity to actually create these guidelines and hopefully improve the best practices. So yeah, I'd just like to share my experience. I've been doing that for more than 10 years. That's pretty much it. So one thing I'd like to emphasize is that even though I'm presenting data science, I'm a geologist first and foremost. I don't just code on my computer. I also go in the field, look at lick rocks. So these are like in the last 12 months, I've been doing greenfield, both in the desert in Saudi Arabia, in the taiga in northern Quebec, or in open pit in looking at different faults in open pits. So first and foremost, what is data science? So the definition of data science is to get insight from data by combining statistics, scientific computing, and scientific visualization. So if you look at this definition, we all do data science. If we upload a data set, we do an average in Excel, and then we do a nice scatter plot. This is data science. So the question, are we data scientists? We're all data scientists. It's just, yeah, different tools that we use. But the goal here is to get insight from data. The insight can be understanding of the data or predictive models. So either getting knowledge from the data or producing more data from the data. There's plenty of different terms that are associated with data science. I'll focus on quickly defining some of them. Machine learning, AI, deep learning, and generative AI. So artificial intelligence, machine learning, so by definition, artificial intelligence, it's computer science that emphasizes on computers performing cognitive tasks. What is a cognitive task? It's a task that has to be completed by your brain, not your muscles. So anything that can be completed by your brain but is completed by a computer, this is artificial intelligence. So again, if you open Excel, you write 1 + 1, Excel answers 2. This is by definition artificial intelligence. So when you see that someone says, oh, we use artificial intelligence to solve the problem, now it's going to sound a little bit less impressive. Machine learning is a subfield of artificial intelligence. The goal of machine learning is to make predictions or classification based on a large number of examples. So artificial intelligence, it can be just the user gives the rules to the computer. Machine learning, it's the computer decides the rule to make predictions. It's going to look at existing data and you ask, okay, with this data, can you please find a way to predict X, Y, or Z? Instead of us saying, this is the way to predict X, Y, and Z. So it's using its intrinsic coding capabilities to find a solution to a problem. So the advantage of that is that they can be, machine learning algorithms can be used to solve multiple problems with one algorithm because they can adapt to a problem. And deep learning itself is a subfield of machine learning that's using a specific type of algorithms that's called neural networks that tend to be capable to solve more complex problems than most machine learning algorithms. So how does a computer learn? I like to simplify it with a simple equation. Let's say that we have a lot of input data or X's. So for example, it's geochemical data and we want to predict something. So rock type, we can say there's a function that takes our x's. So f of function of x's is equal our y, our prediction. Just the one thing machine learning does is it takes example of x's, of y's, and it tries to find the best function to transform your x's into a new y. So I have an example right below where you take silica, magnesium, and the color here is just the name of the rock. Red is basalt, blue is an andesite. And you give these samples, so these points, to an algorithm, and then the algorithm is going to try to map the space silica magnesium in terms of rock type. And you see, I have examples of many different algorithms. Each one has a different way to answer the question, but it's coloring the field in terms of where I think there's a basalt, where I think there is an andesite, and where I'm not so sure I'll put a muted color. So that's all it is. And depending on the problem, you might want to select different algorithms that can solve it differently. So in this case, machine learning or this specific type of artificial intelligence, it makes predictions without a direct human input. I didn't say you need more than 42 or 45 or whatever percent of silica to have an andesite versus a basalt. It figured out this boundary by itself. So it's data-driven instead of knowledge-driven, but still requires upstream supervision in the sense that as a geologist, I said, okay, I'm going to use silica and magnesium because I think these are the right elements to make the differentiation. I didn't provide, I don't know, aluminum, for example. So it's not completely data-driven in the sense I provide the data and I also, I'm the one using the results as a human. So an important aspect of data science, machine learning, AI in general, that has strong implication in geology is that the predictive models and interpretation based on data are generally, or nearly all the time, interpolations, not extrapolations. So we provide data to the algorithm, it's going to learn in this data space. So if I provide all these gray points, it's going to be able to interpret this space of data points. If I wanted to look at a new, after it's been trained, it has looked at the data, I've done my interpretation, I try to predict a new point that's outside of this data space. It's probably going to be wrong because it has never seen this data space. And because it's based on data, of course, data quality, quantity, and biases in the data will, of course, affect the models. And for this reason, a model trained on some data might not perform well on seemingly similar data. And I can give an example where we train a model for detecting the intensity of foliation on core images. And you end up with a model that works really well. And then we used images that were slightly different, a little bit at a lower resolution, a little bit more dark, and then the model wouldn't work anymore. So you have to be really careful with that. And of course, data without context can limit understanding and model performance. That's specifically true for geoscientists because we always have context. We look at the broader scale, broader picture before doing interpretations. And sometimes models cannot do that. So I'll give a few examples of applications of data science in mining-related geology or exploration. And then I'll focus a little bit more on some aspects that are important if we want to use these tools right. So yeah, here's an example of data science, is geochemistry interpretation. So you can use tools such as principal components, clustering, to analyze multi-element geochemistry. So geochemistry usually is hard to visualize as a multi-element data set. You can do ratios, you can do indexes, but at the end of the day, you visualize just one value at a time. You can use these tools to look at all the elements at the same time and try to find patterns. So I show an example here of a deposit where you have, here it's the zinc that's shown, but using multi-element clustering, you can outline using all the elements together, the different domains and patterns within the data, and then try to interpret them. So it supports the interpretation as a geologist you have of the deposit and helps with the visualization instead of relying on one single value. So that helps with the interpretation of complex patterns. And in this case, you can see different zinc enriched, copper enriched, gold zones, and different relationship between these elements. Another example, this time of using machine learning, prospectivity mapping. So prospectivity mapping, it's the exercise of combining different data sets, generally at the regional scale, to help understand where we are the most likely to find new deposits. So the idea is to combine, you have a mineral system model, you know that some specific lithologies are important, some specific sets of faults, you can detect it maybe more with some aspects of the geophysics, but it's hard to look at all of these layers together if you have 10, 15, 20 of them. So you can use data science tools such as machine learning to train on known deposits, existing deposits, and the available data to be able to predict, okay, when I have known deposits, I have this combination of geological settings. The algorithm is going to learn that, and it's going to be able to say, well, I find the same set of geological setting in these other places, so that's where I'm going to be the most likely to find new deposits. So the advantage is to combine multiple spatial data sets. Of course, it requires training. So if you're somewhere you have no known or already discovered deposits, well, tough luck, you can't use this type of approaches. The advantage is that it limits the exploration model bias in the sense that if you're too much biased by a specific idea or genetic model for the deposit, it's going to be able to look at it and tell you, well, no, actually the data doesn't say this is useful, you should use something else. But it still requires very strong domain expertise. When you have geological data, there's 1 million way to prepare it for such exercise. And of course, you're biased by your understanding of the model, and you're not going to provide, for example, faults for some deposit types, but for a lot of others, you're going to provide faults as an input because the structural controls are really important, for example. Another example, this time this is deep learning, automated core image logging. So in this case, we can use computer vision, which is one way to use deep learning algorithms to automate the recognitions of feature on core images. And this example right here is relatively simple, where you have quartz veins, and as a geologist, hopefully you're not asked to log every single quartz vein or veinlet within your project. That would take forever. But for an algorithm that's well trained, that the time doesn't matter. It's super fast, and it's not a hard exercise. Even a non-geologist can be trained to recognize, well, here this is a quartz vein, here as well, and here this is not a quartz vein. So you can see on this on the image to the left, you have the actual core image with the depth on the left. In the center, you have the mask. It's basically the algorithm has been trained to map every pixel. Is it a pixel of vein or is it a pixel of not vein? And simply you have this red line that goes through the middle to measure the from to value of every single vein. So you can export that either as a from to table, here are all my veins, or you can calculate vein density every 5 or 10 centimeter intervals. And then you have a high resolution data set that can be used by the geologist for interpretation. So what it does here is that it reproduces the eye, but not the brain of the geologist. Of course, it's limited to what is on the image. If you can't map something that is not visible to the eye of the geologist on the image, but it can help with automating some menial tasks like looking at every single vein within a large image data set. So the advantage here, it allows high resolution, systematic and reproducible logging of geological or, for example, geotechnical features. So that's, yeah, again, another example of applications of data science. And there are a million others out there, but it just gives an idea of what is possible to be done. I wanted to touch very quickly on generative AI as well, because we use it more and more. So these are advanced complex deep learning models. So they're, as far as I know, all of them are derived from deep learning models. The difference is that they're trained on very large amounts of data. Sometimes it looks like it's the entire internet, like for example, like ChatGPT. What they do is they generate outputs that are supposed to be undistinguishable from the human-made content. So you can't tell or you're not supposed to be able. The goal is for the algorithm to do something that we're not able to discriminate from something a human had done. And it's based on prompts. The prompts can be a text, you give a question, or it can be an image, it can be a sound, and it's going to derive new content from this prompt. So examples are large language models like ChatGPT, or generative adversarial networks that do images like stable diffusions. So the difference with regular or standard machine learning is that regular machine learning will predict a specific outcome. Generative AI will generate plausible data instances. It doesn't try to find the truth. It just wants to generate something that looks plausible. So it's the difference between a simple deterministic output and something that's within a range of possible and consistent with the learning. So on the right is an image created by one of these generative adversarial neural networks. So some examples of generative AI that's used on geoscience related data. This is not my work. This is work from a few friends who are based in Quebec, where they used low resolution mag and high resolution mag in some areas to train an algorithm to use the low resolution mag to predict what the high resolution mag could look like. And then they were able to do the predictions in a lot of different areas. On the right, you can see the model that is training. So you can see the resolution is increasing progressively as the model learns progressively to predict better and better images. So the way it works is that there's an algorithm that's going to try to predict images that are looked like high resolution. And there's another algorithm that's going to be able to say, well, I believe you, I don't believe you. And the first algorithm will try to improve itself until it's able to trick the second algorithm. And as you can see, progressively, it improves. The important point here is that this is generative AI, so it's not showing you the truth, it's showing you a possible truth. And it's always important to remember that when using these tools. Another example, this time using more text-based generative AI, where we used an equivalent of ChatGPT for typo corrections. So again, this is not me, this is brighter people within SRK who completed that, but I asked them to, so I was extracting characters from images. So you can see here information from blocks within core boxes. And I was extracting the whole ID and the depth, but the algorithm, the optical character recognition algorithm, was making mistakes. So I can give examples here. That's what I would have wanted. So whole 19.3, depth of 0.00, and then it was, so for example, instead of 19-3 was 19.3, I already forgot the point in 29.50 right here. It's saying mole instead of whole. H instead of an 8, for example, or Z instead of a 2. As a human, you can, if you look at all of these, you can correct them because you know that after, so depending on the order of the blocks, one block will be higher than the next one and lower than the second next one. So you can guess that, you can guess it's not mole, you can guess it's whole. But the issue is that it's going to take a lot of time to do it on thousands of images. So the idea was to ask ChatGPT or an equivalent to do the correction for us. So it worked relatively well. It's super useful, but the technology is not perfect. Still makes mistakes. So it's not a tool that you can use and not look at it and be happy with the results. But we're getting there, and it's improving every single day. And for someone like me who's lazy, doesn't want to look at do all these corrections manually, that makes the task a lot easier. So I wanted to, it's something I try to put in all my presentation is I want to emphasize the relationship between this type of tools and the geologists. So I give an example from a different domain. So this is a reference from 2012. In many applications, the performance of machine learning-based automatic detection and diagnosis systems has shown to be comparable to that of a well-trained and experienced radiologist. That was 12 years ago. When you go to the hospital, you still have a radiologist. And that's going to be the same thing for geoscientists. These tools are amazing. They can help us do some things better than us, but at the end of the day, they produce just an interpretation. They produce a prediction. You need someone to take this information and do something with it. And that's where we stand. So they are tools for us. They are not replacement for what we do. And I don't believe it's gonna happen anytime soon that we would be replaced by this type of tools. However, it's important to learn how to use it. And of course, there's a lot of challenges in using these tools specific to geoscience. And I'd like to emphasize some of these and to explain maybe some ways to overcome these challenges. So the challenges, the data nature, quality, and format limitation. I think in geoscience, we're really bad at having standard ways to look at data. Give this image as an example where when you look at core images, everyone has a different way to take them, and sometimes it's just not adapted to any automated logging methods, and you just have to discard it, whether it's low resolution or the angle is completely bad. The data is multidisciplinary. How do you compare airborne geophysical data with geochemistry data? It's multi-scale. Same thing if you have some data along a drill hole, that's point data, other that are intervals, how you put all of that together. And we're working in complex systems. Geology is not simple system that can be interpreted very easily, like some things related to marketing, for example, and things like that. It's a lot more complex. So that makes the usage of these tools they require a lot of domain expertise. So yeah, there's a lot of domain expertise that's required to use these tools. You can't just be a data scientist out of the university with no geoscience expertise and try to apply your knowledge to geoscience. It's usually not going to work because there's so many specificities to the data we use and the problems we try to solve. And the last one, but a very important one, is that geoscience has spatial components. So everything we look at, it has relationship with its surrounding. There's relationship that are spatial texture in the data. The fact that when you have a deposit, it's going to be along a fault, but it's going to be related by another deeper fault that goes to the mantle, for example, that's not directly connected to it, but spatially they have a relationship that's super important and that needs to be understood to help with exploration. So spatial variability will limit small usages because it's hard to communicate this information to the tools, to most of the data science tools. So I'll delve into a little bit more detail in all of these challenges and how to address them. So an example of data quality limitations. So first, when training a model, can we rely on subjective data? That's a big issue in geoscience, is we use a lot of subjective data, a rock description. If you ask 10 geologists about a rock description, you'll get 20 different answers. And what do you feel your algorithm to train it? And what do you want your algorithm to predict? Again, the lack of standards on how to collect core images. That means that if you use a model somewhere on a project, it might not work elsewhere because the core images are too different, or simply the method for aquaregial or for acid digestion can vary a lot from a lab to another. The temperature, the timing, that will lead to variable dissolution rate of different minerals. And sometimes you can't even compare the outputs, from different labs. So that will make it complicated. Another example, portable XRF analyzers are often not calibrated. So the results from one portable XRF analyzer is not comparable to one of another. And I give this example right here where I took a shot at a fairly felsic rock. I think it was a rhyolite. I ended up at 14.86% silica. And I think it has to be somewhere around double that. The real value of a rhyolite is somewhere a double around that, but because it wasn't calibrated, it's just giving me this number that would need correction to be meaningful. So without proper data, project can fail, and it's even before it has started. An example of domain expertise requirement, if you want to study, for example, the remote sensing signature of a deposit, you better take a satellite image that's been used before any human disturbances. So I give an example here of the Chuquicamata open pit. If you provide this image to an algorithm, what it's going to learn is just to discover where you have open pits, right? So it's not going to help discover new deposits. The most obvious thing that's specific to this image is the open pits. So yes, you're going to discover a lot of open pits within your area of interest, but you're not going to discover new deposits. It sounds silly to a geoscientist. Of course, we would see that. a data scientist who has not been trained might not to geoscience might not think of it as obvious and might not realize it before it's too late. And I give this example here of when building a regional prospectivity map for gold deposits, one should not include copper assay values in drill holes. And I give this specific example because it's one that actually happened that I saw, where a data scientist, not geoscience training, tried to apply his knowledge to prospectivity mapping. He gave all the drilling information, and big surprise, the algorithm learned that if you want to find a deposit, you need to be in a place where there is a drill hole with some anomalous copper in it, and you're more likely to find a gold deposit there. So what it's going to help you is discover already known deposits, not discover a new deposit that has not been drilled yet. So again, it sounds very simple, but if you don't have the domain expertise, you're not going to be able to sort the data, understand what's important, and what biases the model, and you're going to have the useless results. Another example of advantages of domain expertise, again, for prospectivity mapping. So understanding the available data, understanding what it is, what's the implication, and how it helps to identify the most useful part of the data, especially when you have a lot of it. Apply useful processing and interpretation to the data instead of just using raw data, and deconstruct the problem, sometimes in several simpler problems that are easier to solve, and will lead you to a solution a lot faster. So I give this example right here where you have this table. These are all different layers used for prospectivity mapping exercise. And on the right, you have a AUC score. It's basically a score for this purpose here. It goes from 0.5 to 1. 0.5, the data set is not correlated at all to the deposits I'm looking for. And 1, it's perfectly correlated. So you want the highest score possible above 0.5. And you can see that, so in yellow on the bottom, you have different processed geophysical surveys. Some of them are useful, so for example, the gravity survey, but some of them are completely useless, close to 0.5, processed data derived from the MAG survey. As soon as you interpret the data, you can have a lot more value from the data set. If you interpret specific lithologies, if you interpret structures from this data, you can improve a lot the value of the data set. But who can do that? You need to ask a geologist to do this interpretation. You can't make it up. So it doesn't mean that the raw data or the raw geophysical data is useless. In this case, you can see the gravity survey by itself has a decent AUC score, but sometimes you can create a lot more value when you know what to do with the data, what type of processing, what type of interpretation. How do you include deep domain expertise? I'd like to show one example where I thought it was super successful to use people who knew what they were doing. So this is a case where I was approached by colleagues who are geotechnical engineers and asked me, okay, can we do something with geotechnical logging on the core images? And as a geologist, the first thing I would have thought is, yeah, let's look at breaks and calculate RQD, but they wanted something different, or their aim was a little bit different, and we had to work to build something that aimed at solving their problems, getting the type of data that was useful to them. So instead of reproducing logging parameters that are adapted to manual logging, so for example, the RQD or rock quality designation, we discussed, okay, what are they using the data for? What do they want? And then we did a lot of different tests on things that could work, could not work, and ended up finding specific index or way to look at the core images to help with their problems, and specifically adapted to photo logging and computer vision. So I'll delve a little bit more into it. So first, the standard in the industry, the rock quality designation or RQD index, it's basically the sum of the length of core pieces that are longer than 10 centimeters divided by the total run. You do it over 1 meter, over 3 meters, for example. It's estimated as a percentage. So the lower it is, the poorer the rock, the higher it is, the better the rock quality. The issue is that it's over larger intervals, 1 meter, 3 meters, so the resolution is not that good. and you need to identify natural breaks. And on core images, that's very challenging. I haven't seen any algorithm that can do it reliably unless it's marked manually on the core. So there's a little bit of chalk on the core that says, okay, that says this one is natural, this one is mechanical break. So we wanted to do something a little bit simpler that would not rely on this classification. And when I say we, it's they came up with the core damage index. I was just the data scientist applying their vision to the core images. So it's simply different classes based on the size of the pieces of core in the core image. So disintegrated, it's tiny little pieces of core, heavily broken. The core is smaller than the width of so the pieces of core are smaller than the width of the core. Broken, it's the size of the pieces is the width of the diameter of the core up to, I think, twice the diameter of the core. Partially broken, it's more than twice, and then broken, it's larger than that. The advantage is that you are not limited by the size of the interval, so you can have up to like 5 centimeter large intervals. And it's a lot simpler to interpret and doesn't rely on breaks being natural or mechanical. Of course, it has its limitation, but it's well adapted to images rather than taking something that's adapted more to manual logging. So yeah, the thing is here, you need someone to do the manual labeling of core to train the algorithm. And then you use a convolutional neural network, which is a specific type of deep learning model that's trained on the label to reproduce them. And you have an example on the right of what a model would log on some core images. So that was pretty successful, but because the geotechnical engineers were really involved in how to develop this solution. And the results, the advantage of that was to increase the data density. When you have an open pit, instead of having just a few drill holes with geotechnical information, you had reliable information on the entire open pit. It helped with domaining. It helped with the structural interpretation, where the resolution helped actually see the damage zone of the faults and being able to measure the thickness of faults through a deposit, which is not something you can often do reliably on using master data sets. So that was a really successful example of applying domain expertise to get better results. Another one, or the last challenge I would like to address is spatial issues in data science. So geoscience problems consider spatial relationships between geological features and the issues that it's hard to communicate this information to a model. What are the spatial relationships between different points, samples, or data sets? So we also have the issue of spatial autocorrelation and non-stationarity. That will allow models that are trained or adapted to some place to not perform that well in other places because the data varies, it's different. So for example, a machine learning prospectivity map that was trained and optimized on deposits in a specific location is unlikely to work on deposits in another location. It can work sometimes, but most of the time it's going to not work as well. I give a very simple example of this non-stationarity. This is a paper that I thought was really interesting because they found a diagram to make the difference between different tectonic setting using a simple thorium over tantalum ratio. So here you can read that you can make the difference between continental, active continental margins, so that's continental arcs, and oceanic arcs using this thorium over tantalum ratio. I thought, oh, that's pretty cool. Because at the time that was useful to the project I was doing. And you can see right here, the diagram they have, and you can see that the oceanic arcs plot in this field, the active continental margins plot in this field. The issue here is you can see that the oceanic arcs are mainly from one data set right here, from one location. So you can argue that maybe this diagram is what it's showing is that it's not the oceanic arc versus active continental margin, but it's this specific oceanic arc versus all of these continental margin. So what I did is I took the public data from the GeoRock database, differentiated a lot of samples from a lot of different arcs into oceanic and continental, plotted that, and you can see the same diagram. There's no significant difference in the thorium-tantalum ratio between oceanic and continental arc, and then that means it wasn't useful to the project I was doing. So you have to be careful with these spatial variations. It's something that works in one area might not work elsewhere. So how do you solve a spatial autocorrelation when a non-stationarity when you work on machine learning algorithms? You need to make sure that you keep test data sets that are spatially separated from the training data and that are representative of the type of data you're going to use your algorithm in. And I give an example right here where we used so this is publication from before I was with SRK, where we trained a model on drill hole data. What we did is we selected some drill holes to train the models, but we kept some of the drill holes to test the model. The reason is that all the data that's within one drill hole is going to be very close spatially, so they tend to have spatial autocorrelation. But if you want to see if your model is going to work on new drill holes, new data, you really need to have test drill holes on the side and test the model on it. And I give the example right here. It's not the exact same problem, but that's the exact same idea where it was on different drill holes. If you test on the same data you train your model is, you have 85% accuracy, amazing. Then you test on randomly sampled test data. They can be from the same drill holes as the training data, but they're just separated. Then you get 61.5. Well, maybe your model is not that good, but still could be used. But then when you do this approach to use to test on randomly selected test drill holes, you get to 44.6% accuracy. Yeah, maybe the model is not that good and I shouldn't use it. So if you don't do it properly, you might end up saying, oh, actually my model is pretty good. I'm going to use it. While at the end of the day, maybe you shouldn't, and you should find a better model to solve your problem. And you can do the exact same thing when you work with spatial data, where you divide the area of interest into different sub areas, some of them using for testing, some of them used for validation. Another approach to that, taking into account the spatial context, is using GIS. I've learned through the years a lot about GIS processing, and you can do amazing things. You can do distance maps, density maps, catchment attribution. There's an example right here where we have stream sediment geochemistry. And instead of just attributing the value to points, what we do is we attribute the geochemistry value, the metal anomalies, for example, to a catchment in which the stream sediment value is, and then you have a spatial representation of what is the extent or the area that is affected or that affects the composition of this sample. So it's important to think outside of the box, try to use tools that incorporate the spatial context, or sometimes just use algorithms. So data science algorithms are already adapted to spatial context, like for example, our convolutional neural networks that take images. So they take the spatial context and texture within the images, not just the pixel values. So how to do better data science in exploration and mining geoscience as a reflection on what we've seen above in the presentation. Always review the data quality, try to improve it where possible. And sometimes it's good to say, well, actually the data quality is not there. Do not use the data if the quality will compromise your interpretation. Identify that early on instead of being sorry after spending many hours trying to solve a problem. One important one, something I had to learn, and I'm still trying to not be too biased in here, is identify a problem and then find the tools to solve it, rather than adapt a tool and try to solve every problem with it. When you learn how to do machine learning, for example, everything can be solved by machine learning, or you think so. That's not the reality. And it's important to stay open to, okay, what am I trying to solve? And maybe there's something out there. Ask your colleagues, ask other people, how would you solve that? They have a lot of expertise in different fields, and maybe they'll know something you don't. Integrate stakeholders, including domain experts in the data used as input, whether it's geophysics, geochemistry, whether it's for geotechnical, geological purpose. Make sure to have people who know what they're talking about to help you. That will save you a lot of time, and that will help you be successful. Always test your results using data science and geoscience metrics. When you build models, there's always a data science metric that's going to be this value from 0 to 1 that tells you how well your model performs. But it's always good to have sanity checks to plot the data in space, to look at it geologically. Does it make sense? Is it what I expected? If not, why? And keep up with innovation. As I said at the beginning, this is a very fast evolving science. The best practices are evolving with time as well. There's new tools, there's new cool things to adopt, and there's always ways to improve the way we work. And one important one as well is try to solve problems on toy data sets before doing it on complex data sets. So a quick example on the core images for vein logging. The first time I did it, I was asked by a client, can you do it? I didn't know, so I took 50 images of veins, spent 40 hours trying to find the best model to do it, finally found it, and then I was able to say, yeah, I can do it. And then apply it on real life images instead of trying to start right from the beginning from the entire data set, complex data set provided by the client. So the conclusions, data science, machine learning, AI, they're, in my view, amazing innovations in mineral exploration, mining, geology. They help to do a lot of things, but are not revolution. They don't replace the geologists. They don't change completely the way we do it. They just need to be integrated in our current workflows, best practices, and help improve what we do. And also they allow thinking outside of the box, generating solutions that are adapted to our challenges, instead of just reproducing the way we've been taught to do things. So they're really good tools to improve the way we do things. And yeah, that's the conclusion. So yeah, hope you liked it.
Thank you so much. It was awesome having you on.